In this video, we're going to talk about valence bond theory. We're going to do this in context of molecules that have a steric number of 4. And the good example we can use there is the bonding in methane. So CH4 is methane. Let's start with the Lewis theory, since valence bond theory really presumes Lewis theory to start. So let's look at what Lewis theory tells us about bonding in CH4. We know from Lewis theory that the dot structure of carbon is 4 dots, 1 on each side, and then hydrogen with its single valence electron has just 1 dot. So carbon 4 valence electrons, hydrogen 1. And what Lewis theory tells us is that covalent bonds between 2 atoms, nonmetals, shared electron bonds, are formed whenever an atom has a single electron on one side. So for example, carbon has 4 single unpaired electrons on each of its sides, and hydrogen has 1 unpaired electron. So I would expect that carbon would be capable of forming 4 covalent bonds with other atoms, while hydrogen should be capable of forming only 1 covalent bond with any other atom. Now the molecule we're looking at here is CH4. Carbon's a central atom. So what Lewis theory tells us is that each one of our bonds is going to be a single bond between carbon and hydrogen, and each of those bonds will consist of a pair of bonding electrons. What we also know is the molecular geometry of CH4. And what VSEPR theory tells us is that all 4 bonds are equivalent, and this is borne out by experimental measurements, and that the molecule is tetrahedral with bond angles of about 109 degrees. So we can draw the 3-dimensional structure of methane like this. Whenever we show a solid wedge, what we're meaning is that the hydrogen on that solid wedge bond is coming out of the plane of the paper, and the dashed line means that the hydrogen is behind the plane of the paper. Now, the other thing we also know going into valence bond theory is the quantum theory of the electron energy levels in the atom. Now, we've done this in other videos, so I'll only go through this very quickly. But we can make on an energy scale, the vertical from top to bottom with increasing energy, we can lay out the energy levels of the atom, the electron in the atom. So we know that the lowest energy level is 1s. Then we've got 2s and 2p. 3s, 3p, 3d, 4s, 4p, etc. So we could keep going, but this is enough for the purposes of the discussion we're interested in here. If we're talking about hydrogen with 1 electron, we would put that electron in the lowest available energy orbital, which is 1s, so there would be 1 electron there. We'll show the electrons as arrows, which is to indicate the spin of the electron. We can either have a positive or negative spin, and we'll use up and down arrows to show the opposite spin of paired electrons. So hydrogen would look like this. If we're talking about carbon, we need a total of 6 electrons, so let's put those in. The second electron also goes in 1s to form the pair there. The next 2 electrons in 2s, and finally the last 2 electrons will go in 2p. Whenever I have a situation like I do with the 2p orbitals where all 3 have equivalent energy, I know that 1 electron will go in each orbital before I would begin to pair them up. That's slightly more favorable in energy than pairing up the electrons into a single orbital. Now, what we're interested in for bonding is only the valence electrons. So we don't need to consider the 1s electrons. Those are there, but they're in the core. So we're not going to consider those. So we'll X those out. And the valence electron orbital energy diagram looks like this. So I have only 4 valence electrons. I have my pair of electrons in 2s, and then my 2 single electrons in 2p. We also know the shapes of the orbitals. What quantum theory tells us is that electrons in atoms don't exist like little marbles orbiting some central sun, like little planets around a nucleus. But in fact, the orbitals are wave functions. And what we mean by that is that the electrons can be understood as being like waves. So I can tell you the probability of where I can find the electron. So I know with 90% certainty the electron is in some sort of spherical envelope that looks like this. And for the two p orbitals, what their wave functions look like is two lobes. And the red lobe is one that we can consider to be positive. So we can write a plus sign there. And the negative lobe, the blue lobe, would be down below. So each one of those would be two separate signs. The wave function changes signs whenever I have a node. There's a node right at the nucleus. So this p orbital has two lobes, one plus and one minus. The px orbital is oriented along the x-axis. The py orbital is oriented along the y-axis. And the pz orbital is oriented along the z-axis. So what I know is that these three p orbitals exist at 90 degrees relative to one another. So the p orbital has some directionality to it, while the s orbital does not. So before we start discussing bonding, we know all of these things about the quantum theory of electron energy levels in the atom. The other thing we know to start out is a very simple picture of what bonding looks like. So early in the days of quantum theory, just a couple of years after the discovery of quantum theory in the mid-20s, a mathematical solution was worked out for the electron energy levels and the wave functions of the electrons in the hydrogen molecule. Now we know from Lewis theory that hydrogen consists of a single bond between two hydrogen atoms. Each hydrogen having a single unpaired electron can form a single bond. So when those bond together, what Lewis theory tells us is that the bond looks like this. I have two electrons shared between the bond atoms. What quantum theory tells us is the way this bond forms is by combining the 1s orbitals on each of these hydrogen atoms. Now we know that each hydrogen has one electron, which is what Lewis theory has told us. We also know from quantum theory that that electron sits in 1s orbitals. So the way the bond forms, according to the quantum theory of molecules, is that I combine these two wave functions together, and they do what we call overlap. And when those overlap or add together, what I get is a bonding orbital that belongs to that entire molecule. So the covalent bond in quantum theory is formed by combining wave functions from the two bonded atoms to form a bonding orbital. And if I have a single bond, we'll call that a sigma bond. So we use the Greek letter sigma to denote a single bond in quantum theory. And since each hydrogen contributed one electron apiece, this sigma bonding orbital in H2 contains our two electrons in the molecule. So all of these ideas together form the basis for valence bond theory. Now let's look at what valence bond theory tells us about the bonding in CH4. Remember, we've got to be able to come up with a quantum theory of bonding in CH4 that is consistent with everything we know. We need it to fit Lewis theory, the idea that carbon is capable of forming 4 covalent bonds. And we know each one of those bonds is a shared pair of electrons between the two bonded atoms. We need the valence bond theory to justify the molecular shape of CH4, this tetrahedral shape with bond angles of about 109 degrees. And we need to describe the bonding between each of these atoms as involving an overlap of atomic orbitals from each of those bonded atoms. Now for hydrogen, we did H2, so we already know that the orbital that is going to participate for bonding between carbon and hydrogen will be 1s on the hydrogen, but for carbon we're not sure. So that's the mystery that we need to solve first, is what orbitals in the carbon atom are involved in forming this bonding orbital between carbon and hydrogen. So leaving all of our pieces that we need to justify, let's put together what we would expect to get based on the quantum theory of the valence orbitals or the valence electrons of carbon atoms. So here's what we already know from quantum theory about a free carbon atom. That is a carbon atom with no other atoms around, no bonds, just a single carbon atom floating in space that we'll call the free carbon atom. I have 2 electrons in a spherically shaped 2s orbital, and I have 2 individual electrons, each in 2 of my p orbitals, the third orbital being blank. And which one of these is containing an electron in px, py, pz, I can't be sure, but I know that 2 of the orbitals contain 1 electron each. Now, if I were to look at what Lewis theory tells us, it's that I should only be able to form bonds when I have a single unpaired electron sitting in an orbital somewhere. So what I would expect if carbon, when it's in the molecule CH4, bonded to 4 hydrogen atoms, if the electron configuration of that carbon is exactly the same as it is in the free atom, I should really only be able to form 2 bonds. And remember that these electrons, which are sitting in my diagram in the px and the py orbitals, are at a 90-degree angle to each other. So I would expect the bond angles in those 2 bonds that I would form with carbon should have a 90-degree bond angle. So obviously this particular picture of the quantum theory of carbon, of the free atom, isn't going to be able to describe what I see in CH4. I wouldn't be able to get 4 bonds, the bond angles would not be 109 degrees, and there's not enough orbitals there to overlap with hydrogen 1s to give me the 4 bonds that I need. Now, what Linus Pauling, who developed valence bond theory, realized is that there's no reason to believe that a free carbon atom with no other carbons around, floating in space by itself, is going to have the same electron configuration as a carbon atom in a molecule like CH4. Once that carbon atom is bonded to 4 other atoms, it's reasonable to believe that some of these orbitals may change in energy, and the occupancy of these orbitals will change as well. So what Pauling proposed is that the carbon atom in CH4 doesn't have this free electron configuration that we're showing on the top right, but instead undergoes a process called orbital hybridization. And the word hybridization means simply combining 2 things or more things together to get a new thing. So what Pauling proposed is that I get a combination of the wave functions, the 2s, the 2px, the 2py, 2pz, and since I'm starting with 4 functions going in, I need 4 functions in my final result. So what I get is 4 new orbitals that I'll call sp3 hybrid orbitals. These are formed by what we call linear combinations of the atomic 2s and 2p orbitals of carbon. So there's a lot to unpack there. We've defined what hybrid means, combinations. I have 4 equivalent orbitals. I call them sp3. The reason I do that is because each one of these orbitals is going to consist of 3 parts of p wave functions and 1 part of s. So what I mean by sp3 is that each of my hybrid orbitals is going to be 1 part s and 3 parts p. And I form these by linear combinations of these atomic orbitals. The other thing we need to unpack is, what does a linear combination mean? Well, that's just simply a mathematical term. Remember that I can treat these electron orbitals, wave functions, as I can any other function. And what quantum theory tells us is that when it's possible, that the wave functions can combine together to form a new set of wave functions, which is exactly what's going on in the orbital hybridization process. So let's consider what we mean mathematically by a linear combination of wave functions. In mathematics, the term linear combination has a very simple meaning. Let's suppose that I want to form a function by combining 2 existing functions. So a linear combinations mean I'm going to add those 2 functions together with a coefficient of some kind. Now let's take an example. Let's suppose that one of my functions, f1, is just simply x equals 3. Now it doesn't have to be that, it could be anything, but for an example, let's just pick f1, our function f1, to be x equals 3. So this is one of my functions here. The other function, maybe it's a little bit more complicated. So let's say that that function is square root of 2 times the quantity x squared plus 6x minus 7. Now, it doesn't really matter what functions I choose, but for an example, I've got to pick something. So let's pick these two. What I'm going to do is to form a new function by combining f1 and f2. So I'll do that by taking my new function, which I'll call just f of x. And it's going to consist of 1/2 of the f1 function plus 1/2 of the f2 function. Now the two coefficients don't have to be equal, but I could have f of x, maybe it's only 0.33 or 1/3 of f1, and maybe it's 2/3 of f2. But what I mean by linear is that I can't have something that looks like this. I can't have 0.5 times f1 squared plus 0.67 times f2 squared. That wouldn't be a linear combination. So linear means that each of these functions that I add together to get my new function, f of x, has to be taken to the first power. So it's understood that I mean f of x equals 0.33 times f1 to the first power, 0.67 times f2 of x also to the first power. Now I can do the same thing with wave functions in the atom, and that's exactly what I've done in the orbital hybridization process. In that case, the new function I'm forming is the hybrid orbital wave function, and the functions that I'm forming them from will be the 2s and the 2p orbitals of the carbon atom. So let's see what that looks like. So let's start on the left of this diagram with our orbitals for the free carbon atom, 2 electrons in 2s, and 2 electrons in each of my 2p orbitals, with the third one being empty. After orbital hybridization, I get my 4 equivalent sp3 hybrid orbitals that are formed by a linear combination of my atomic 2s and 2p. So let's look at one of these wave functions. So let's pick one of them. The one thing I notice is that they're all 4 equivalent in energy, which is why I show them to have the same level on a horizontal scale. So this is an important part of my diagram, that all 4 will have the same energy. To get 4 equivalent bonds, I need to have all 4 of those orbitals be equivalent. So let's look at one of them. So I'll look at this one. So mathematically, let's see what that looks like. So what I'm going to do is take 1/4 or 0.25 times my 2s orbital. I know that wave function is a sphere. I'm going to add to it 3/4 of my 2p orbital set. And I know that that looks like this, with one of my lobes being positive and one of them is negative. Over here, I don't have lobes for my 2s, so I just have a positive lobe. So when I take a linear combination of 1/4 2s plus 3/4 2p, when I combine those together, I have out of phase overlap, or plus to minus, with the lobe on the left, and I have a positive overlap of the 2s orbital with the positive lobe of 2p on the right. So what that's going to do is on the left, I'm going to get an overall larger lobe, where I've combined those two wave functions together, plus to plus. And on the left side, where I've combined them together, plus to minus, I'm going to get a smaller lobe. So my 2p3 hybrid orbital looks like the orbital on the upper left, with one very large lobe, and that's going to be the one that points toward the atom to which I'm forming a bond, in this case the bond to hydrogen, and the very small lobe behind the atom. So again, remember my nucleus is dead center here, so it's right here. The small lobe behind the nucleus is not going to participate in bonding. It's this much larger lobe right here that's going to participate in bonding. Now let's look at what each of those CH bonds look like. I know because I have 4 equivalent sp3 orbitals, all 4 with the same energy, and all 4 of them have 1 electron each, that I'm going to be able to form 4 bonds. What each one of those CH bonds looks like is an overlap, which I know from quantum theory is what happens when bonds form. I take one of my sp3 orbitals on carbon, I overlap it with my 1s orbital of hydrogen, and these two together form a CH sigma bonding orbital consisting of the carbon sp3 hybrid plus the hydrogen 1s. So that's what valence bond theory tells me that bonding orbital looks like. Now, the other thing that's interesting that falls out of the mathematics is when I combine 1/4 of my 2s orbital plus 3/4 of my 2p orbital together to form this hybrid, what I find is that the 4 hybrids that I form are directed toward the corners of a tetrahedron. The angle between them is exactly 109.47 degrees, exactly what I need it to be to get the overall bonding in CH4. So while each one of my bonds look like this, when I put them all together to describe the entire molecule of CH4, here's what I get. So each one of these is an overlap of carbon, which is at the center. So the carbon nucleus is right here in the center. I see the tiny lobes, which are not participating in bonding. I see an overlap between this lobe of the sp3 hybrid of carbon with this hydrogen 1s. I see the same thing up here. I see the same thing here. And I see the same thing here. So this is the success of valence bond theory. In forming these orbital hybrids of carbon, I arrive at the conclusion I need, that I form 4 carbon-hydrogen bonds because I have 4 identical energy orbitals with 1 electron each on carbon. The bond angles are 109 degrees because each of these hybrid orbitals is directed at 109 degrees of separation from one another. And I form the bonds by overlap of 2 atomic orbitals. In one case, the sp3 hybrid orbital on carbon. In the other case, the hydrogen 1s orbital on hydrogen. So I fulfill all of my requirements because I allow orbital hybridization to take place. So that's the key to valence bond theory, is forming these hybrid orbitals, which acknowledges that the electrons in the carbon atom within the CH4 molecule don't necessarily have to be exactly the same as the electrons in the free carbon atom over here. Next, let's look at valence bond theory of the bonding in water. So remember, water also has steric number 4. The reason it has steric number 4, remember what steric number is 2 bonded atoms. So my oxygen is bonded to 2 hydrogen atoms. And in addition to that, I have 2 unshared pairs of electrons. So my steric number consisting of 2 bonded atoms to oxygen plus 2 unshared pairs of electrons in oxygen means steric number 4. So to describe the bonding in water, using valence bond theory, we're going to go through exactly the same process we went through for CH4. So we'll start with the valence orbitals of the central atom, oxygen. So I have the 2s and the 2p orbitals for oxygen just as I did for carbon. But now, since oxygen has 6 valence electrons, my electron configuration looks like this. So I have 2 electrons in 2s, 2 electrons shared in one of my 2p orbitals. So I have a shared pair here. And I have single electrons here and here. Now, once again, since I have single electrons in the p orbitals, and I know that those are directed at 90 degrees to each other, what I would expect if bonding occurs without orbital hybridization is that these 2 bonds to oxygen from hydrogen would have a bond angle of 90 degrees because that's the bond angle between my 2p orbitals. I know, however, that the bonding in H2O is not 90 degrees, but is much closer to the 109 degrees that I found in methane. So for that reason, I'm going to form the orbital hybridization. I'm going to go through the orbital hybridization process again. I'm going to get my 4 equivalent sp3 hybrid orbitals for oxygen, just as I did for carbon. But why is that? Well, the reason is that because the valence orbitals in carbon are the same as the valence orbitals in oxygen, my orbital hybridization is going to be exactly the same for both. What's going to be different, however, is the number of electrons. So I see that in my hybrid orbitals, 2 of them are going to have a pair of electrons, and those are going to correspond to my non-bonding pairs of electrons here in the Lewis structure. And then I'm going to have single electrons here and here that I can use to form my bonds to hydrogen. So what valence bond theory would predict with the orbital hybridization process is that I should be able to form two covalent bonds to oxygen, and that the separation between those bonds, or the angle between them, would be about 109. Now let's look at what the orbital hybridization process looks like. It's exactly the same as it was for carbon, because the orbitals are the same. So my hybrid orbital consists of 1/4 of the 2s orbitals, plus 3/4 of the 2p orbital. I'm going to combine them together in the same way. Remember that I don't have any lobes in the 2s. I do, however, have lobes in the 2p, so I have a plus and a minus. So when those combine together, what I get is my same sp3 hybrid orbital. So the hybridization process is exactly the same. Each one of these hybrids consists of 1 part s and 3 parts p, which is why I call it sp3. I describe bonding between oxygen and hydrogen the same way as I describe bonding between carbon and hydrogen. I take one of my oxygen sp3 hybrid orbitals and let it overlap with the hydrogen 1s orbital. So this OH sigma bonding orbital is simply a combination of the oxygen sp3 plus the hydrogen 1s. So putting all this together to form a molecule, what I get is my 4 hybrid orbitals. 2 of those are used for bonding to H, and 2 of them are used to contain my unshared pairs of electrons. And the overall geometry is approximately tetrahedral. Now I know that the bond angle in H2O is a little bit smaller than 109, it's about 104.5, but approximately 109 is fine for our purposes here. So once again, the valence bond theory description of bonding in water is successful. And I find that steric number 4 for CH4, steric number 4 for H2O, my central atom in each case is going to have sp3 hybrid orbitals. But generally speaking, if I have steric number 4, that means that the central atom will have an orbital hybridization of sp3. The bond angles would be approximately 109. We went through in detail how that worked for CH4 and for H2O. That same analysis is also going to apply to all of these molecules. Let's go through them one at a time. So NH3, nitrogen, steric number 4 because I have 1 unshared pair of electrons plus 3 bonded atoms. Nitrogen in the ammonium ion, I have a central nitrogen surrounded by 4 hydrogen atoms with a central plus charge on nitrogen. In the CF3Cl molecule, carbon has a steric number of 4, so it will have sp3 hybrid orbitals. In OF2, just like in H2O, my oxygen has 2 unshared pairs of electrons, plus 2 bonded atoms, steric number 4, sp3 hybridization, bond angle about 109. And lastly, in NF3, I have 1 unshared pair of electrons around nitrogen, plus 3 bonded fluorine atoms, steric number 4, nitrogen will have sp3 hybridization. The bond angles in NF3 will be about 109. So valence bond theory has a perfect correlation between steric number and orbital hybridization. We've seen in this video what happens when the steric number is 4. We get sp3 hybridization and bond angles of 109. In subsequent video, I'll look at the situation of valence bond theory for steric number equals 3.